Welcome back to the Bureau of the Unexplained, where we dive into all things weird and unexplained. Right now, as you sit listening to this, you probably feel perfectly stationary.
Yeah, you feel like you're just sitting still.
Exactly. You might be sitting in an office chair or driving down the highway, or maybe you're just going for a walk. And the ground beneath you feels completely solid, fixed, and still. But you aren't sitting still, not even close.
No, you're actually moving at incredible speeds.
Right. The Earth is rotating on its axis, moving at roughly 1,000 miles per hour at the equator. And at the exact same time, it is orbiting the sun at about 67,000 miles per hour.
Which is already hard to wrap your head around.
It is. And the sun, in turn, is dragging our entire solar system around the center of the Milky Way galaxy at a blistering 500,000 miles per hour. And the Milky Way itself, our entire galactic home, is hurtling through the vacuum of intergalactic space at roughly 1.3 million miles per hour.
Yeah, that comes out to roughly 631 kilometers every single second.
Every single second. But here's the multi-billion-dollar question. Where exactly are we going?
That is the big one.
Because for decades, astronomers realized that we, along with hundreds of thousands of our neighboring galaxies, are being relentlessly pulled toward this terrifying, invisible anomaly, an area of space simply called the Great Attractor.
Right, and it really remains one of the most compelling gravitational mysteries in modern cosmology.
Oh, absolutely.
The mission of this deep dive is to explore this massive anomaly, to really understand this densely obscured region of space known as the zone of avoidance, which, by the way, completely hides this thing from our view.
Yeah, totally blocks it.
And ultimately, we want to uncover the true architectural skeleton of our local universe. So we're going to map out the cosmic web, going from the invisible scaffolding of dark matter to the most recent supercomputer simulations that are basically trying to predict the ultimate fate of our galaxy.
Okay, let's unpack this, because we have a massive amount of ground to cover today.
We really do.
We're going to dig into the historical observations from the 1970s and 80s, the fluid dynamics of the early universe, data from cutting-edge radio telescope arrays pulling back the curtain on deep space, and some really mind-bending digital twin simulations from 2025 and 2026 that recreate our reality inside a machine.
It's some incredibly cool science.
It really is. But before we get into the heavy physics of how matter collapses, I want you, the listener, to visualize our situation. Imagine you are sitting inside a car, zooming down a highway at top speed.
Okay, I can picture that.
You can feel the intense acceleration pressing you back into your seat. You know you are moving incredibly fast, but the windshield of this car is completely blacked out, just painted over.
That sounds terrifying.
Right. You cannot see what is pulling you, you can't see the road, and you have no idea where you are headed. And that is exactly where humanity finds itself today. We're the driver's seat of the Milky Way, but our windshield is pitch black.
Well, the blacked out windshield is a highly grounded way to think about the zone of avoidance. But before we talk about why we can't see the destination, we really have to talk about how we even know we are moving in the first place.
Yeah, how did we figure out the speedometer?
Exactly. This brings us back to the late 1970s and early 1980s. During this time, astronomers were realizing that the universe wasn't expanding quite as smoothly as the textbooks suggested.
Right.
Because the baseline understanding, ever since Edwin Hubble's observations in the 1920s, was that space itself is expanding. On the grandest scales, every distant galaxy is moving away from every other galaxy. We call this phenomenon the Hubble flow.
Right, the standard model of cosmic expansion. Basically, the further away a galaxy is from us, the faster it appears to be receding. Simply because there is literally more expanding space between us and them.
Exactly.
It's a very neat, predictable mathematical rule.
Right.
Like if you measure the distance, you can predict the recession speed.
Well, that was the assumption anyway. But galaxies also possess what astrophysicists call peculiar velocities.
Peculiar velocities.
Yes. These are localized physical movements caused by the gravitational pull of neighboring mass. And this is completely independent of the background expansion of the universe. So, to measure our specific peculiar velocity, scientists turn to the cosmic microwave background, or the CMB.
Which is the afterglow of the Big Bang.
Right.
But let's clarify what that actually looks like to an instrument. Because when we say afterglow, we aren't talking about visible light, right?
No, not at all. We are talking about microwaves. So about 380,000 years after the Big Bang, the universe had cooled just enough for protons and electrons to combine into the first neutral hydrogen atoms.
Okay, so things finally settled down.
Right. This event is called recombination. It allowed light to finally travel freely through space without endlessly bouncing off a dense plasma.
Oh, wow.
Yeah, and that light has been traveling for over 13 billion years, stretching out as the universe expands and cooling down to microwave frequencies. Today, it permeates all of space at a temperature of about 2.7 Kelvin, which is just barely above absolute zero.
So it's everywhere.
Everywhere. When we point microwave receivers at the sky, this background radiation should look identical in every single direction. It is the ultimate static backdrop of the cosmos.
But it wasn't identical, right?
Oh, it wasn't.
When astronomers mapped it out, they found this massive anomaly, a dipole. Basically, one half of the sky looked slightly different than the other half.
Yes, exactly. They measured a distinct Doppler shift in the CMB. In one very specific direction, the radiation was slightly blue shifted, meaning the microwaves were compressed, making that region of the sky appear about 3 millikelvin hotter than the average.
And on the flip side,
In the exact opposite direction, the radiation was red-shifted, stretched out, making it 3 millikelvin cooler.
so it's basically the classic ambulance siren effect, but with light instead of sound.
That's a perfect way to describe it.
Like, when the ambulance drives toward you, the sound waves bunch up and the pitch gets higher. When it drives away, the waves stretch out and the pitch drops. So because the CMB in front of us is blue shifted, it means we are actively driving into the ancient light of the Big Bang and driving away from the light behind us.
Right.
That dipole is basically our cosmic speedometer.
And that speedometer gave us a highly precise number. It proved that our local group, which includes the Milky Way, Andromeda, and a few dozen smaller dwarf galaxies, is moving relative to the foundational background of the universe.
At what speed?
At roughly 631 kilometers per second, we are quite literally sliding through the expanding space.
But it wasn't just us, right? Like, it wasn't just the Milky Way going rogue. You had a famous group of astronomers in the 1980s known as the Seven Samurai.
Yes, the Seven Samurai.
They were running this massive survey of elliptical galaxies trying to figure out if our neighbors were moving too.
And the Seven Samurai survey was a monumental undertaking for its time. I mean, they didn't have the automated robotic telescopes or the massive computational power we have today.
Yeah, doing that in the 80s must have been brutal.
It was. They had to manually measure the distance to hundreds of elliptical galaxies and then measure their redshift to separate the universe's expansion from the galaxy's actual physical motion.
I want to pause here because doing that without modern tech is insane.
Yeah.
How do you actually figure out the distance to a galaxy without relying on redshift?
That is a great question.
Because if redshift is contaminated by their peculiar motion, meaning they're physically being pulled towards something, you can't use it to gauge distance accurately, right?
That is the fundamental problem they had to solve. To bypass the redshift issue, the Seven Samurai utilized something called the dn sigma relation.
The dn sigma relation.
Yes. This is an empirical relationship specific to elliptical galaxies. They found that there is a predictable correlation between the physical diameter of a galaxy, how big it appears on the sky based on its surface brightness, and its velocity dispersion.
Velocity dispersion.
Right, which is just how fast the stars inside that galaxy are buzzing around its center.
So if you can measure how fast the stars are swirling inside a galaxy, you know its intrinsic true size.
Exactly.
And if you know its true size, you can look at how small it appears in your telescope and calculate exactly how far away it is, just geometrically.
Correct. And once they had the true distance, they could calculate what its standard Hubble expansion speed should be.
Oh, that's clever.
Yeah. If the galaxy's actual observed redshift showed it moving faster or slower than that baseline, the difference was its peculiar velocity, its physical motion through space.
And what did they find?
When the Seven Samurai applied this technique to hundreds of galaxies, the results were just stunning. They found that a massive swath of our local universe, an immense collection of hundreds of galaxies, was all caught in the exact same gravitational current.
We were all flowing together like water in a massive cosmic river.
Precisely.
And if there is a river, there has to be a waterfall. All these galaxies were being pulled toward the exact same point in space. The samurai mapped these velocity vectors, pointed down the stream, and realized there must be an astonishing, incomprehensible amount of mass localized in one spot to generate that kind of gravitational pull.
Tens of thousands of galaxies worth of mass.
Which is just staggering. They dubbed this theoretical leviathan the Great Attractor, And based on their math, it was sitting roughly 150 to 250 million light years away from us.
Which is relatively close on a cosmological scale. I mean, it is firmly within our extended cosmic neighborhood. You would assume that if something possessing the mass of tens of thousands of galaxies was sitting just 200 million light years away, we could simply aim our telescopes at that exact coordinate and see it blazing with starlight.
Right, exactly. We know we're moving, we know the speed, and thanks to the Seven Samurai, we know the exact coordinates of the destination. So why was this a mystery? Why couldn't we just take a picture of it?
That brings us to the zone of avoidance.
Right. This is the massive, frustrating roadblock in this whole story.
The zone of avoidance is the astronomical equivalent of your blacked out windshield. The issue is our specific vantage point. Our sun is located within the galactic disk of the Milky Way, roughly 27,000 light years from this supermassive black hole at the center.
So we are deep inside the disk.
Deep inside. When we look up or down, perpendicular to the flat disk of our galaxy, we have a perfectly clear view out into the deep cosmos. But when we try to look horizontally, directly through the plane of the Milky Way, our view is catastrophically blocked.
Let's contextualize that for a second. It's like trying to look at a distant mountain range, but there happens to be a brilliantly lit, incredible, dusty, smoke-filled baseball stadium directly in front of you.
That's a great analogy.
Our own Milky Way is that stadium. The galactic plane is absolutely choked with dense clouds of interstellar dust, cold molecular gas, and billions upon billions of overlapping stars.
And the interstellar dust is the primary culprit here. These are microscopic particles composed of silicates, carbon, and ice. To visible light, these dust clouds are essentially opaque.
Why is that?
The physical process at play is scattering and absorption. The visible light photons traveling from distant galaxies hit these dust grains, which happen to be roughly the same physical size as the wavelength of visible light.
Ah, so they crash right into them.
Right. The photons get scattered away or absorbed and re-emitted as heat. As a result, almost no visible starlight from the universe beyond can penetrate the galactic plane and reach our telescopes. This band of obscuration blocks about 20% of the entire extragalactic sky.
20% of the universe is just totally hidden behind our own galactic furniture.
Yes.
And in a stroke of profound, almost suspicious cosmic irony, the Great Attractor happens to lie exactly behind this dusty galactic disk, right in the direction of the Centaurus and Norma constellation. For a long time, the region pulling us was quite literally a blank spot on our star maps. Astronomers were tracking these massive gravitational currents flowing into a region of space that simply did not exist to optical telescopes. We were being dragged into the dark.
And the inability to see what was pulling us led to a period of intense speculation. Some theories really pushed the boundaries of standard cosmology. Because we couldn't measure the mass directly, there were questions about whether the pull was coming from something far stranger than a cluster of galaxies.
Which brings up the concept of dark flow. I was digging into some of the research from 2008 by Sasha Kashlinsky and his team at NASA.
Yes. Dark flow.
They weren't just looking at our local 200 million light-year bubble. They looked at the motion of massive galaxy clusters up to 3 billion light-years away. And they found a streak of irregularity. These incredibly distant clusters seem to be moving in a uniform direction as well, pointing generally toward the same region of the sky.
Now, the dark flow hypothesis was and remains highly controversial within the astrophysics community. The core of Kashlinsky's argument was that this uniform, large-scale motion of galaxy clusters, this coherent flow across billions of light years, could not be explained by any realistic mass distribution within our observable universe.
Wait, pause. If it can't be explained by mass in our observable universe, does that mean the thing pulling us is outside the universe? How is that even physically possible?
Well, not outside the universe itself, but outside the observable universe. Those are two very different boundaries.
They distinguish those for me.
The observable universe is a sphere centered on Earth, limited by the speed of light and the finite age of the universe. Because the universe is 13.8 billion years old, we can only see light that has had 13.8 billion years or less to travel to us.
Right.
Beyond that spherical boundary lies the cosmological horizon. There is certainly more universe out there, filled with more galaxies, but its light simply hasn't reached us yet.
Okay, so how could something we can't see, something whose light hasn't even reached us, exert a physical pull on us today? Gravity travels at the speed of light. If the light hasn't reached us, the gravity shouldn't have reached us either.
You are touching on the exact reason why the theory invoked cosmic inflation.
Oh, the early universe stuff.
Yes. In the very first fraction of a second after the Big Bang, the theory of inflation suggests the universe expanded exponentially, faster than the speed of light. Before that rapid expansion, all the matter in the infant universe was crushed intimately close together.
So they were already interacting.
Exactly. The matter that currently makes up our local galaxies was gravitationally interacting with matter that was subsequently blasted far beyond our current observable horizon. The dark flow theory speculates that the uniform motion we see today is a fossilized remnant of that ancient gravitational tug, a momentum imparted before inflation separated everything.
So dark flow is suggesting that the ghost of a monstrous structure pushed far beyond the edge of our reality is still subtly dragging us through space. That is legitimately mind-bending.
It is a fascinating idea, certainly.
The dark flow theory relies on things we fundamentally cannot see. To actually solve the mystery of the Great Attractor, we had to figure out a way to map the room with the lights turned off. We need to see through the zone of avoidance.
Exactly.
So how did astronomers actually manage to peer through the dust of the Milky Way?
Well, they had to change the type of light they were using to look at the sky.
Makes sense.
If visible light photons are being blocked because their wavelengths are roughly the same size as the dust grains, the solution is to observe the universe using electromagnetic wavelengths that are dramatically different in size.
Like what?
You pivot to X-rays, which have incredibly short wavelengths, and radio waves, which have incredibly long wavelengths.
It's like ocean waves hitting a pier. If you have tiny, choppy little ripples like visible light, they splash against the wooden pylons of the pier and get scattered. But if you have a massive, rolling tsunami wave, like a radio wave, it just washes right past the pylons as if they aren't even there.
That is an apt visualization.
The radio wave is so huge, it ignores the tiny dust grains.
Right. By the late 1990s and 2000s, technology had advanced enough for astronomers to launch sophisticated X-ray satellites and build massive ground-based radio telescope arrays. They began aiming these specialized instruments directly into the thickest parts of the zone of avoidance.
And they finally rolled down the blacked-out windshield.
What's fascinating here is what they found profoundly shifted our understanding of cosmic architecture.
What did they see?
They didn't find a single, solid, unimaginably dense object. They didn't find a localized supermassive black hole. Instead, as the X-ray and radio data poured in, they revealed sprawling, complex structures of thousands of galaxies.
Wow!
The first major discovery sitting right near the predicted center of the Great Attractor was the Norma cluster, officially cataloged as Able 3627.
I was reading about this. The data on the Norma cluster paints a picture of extreme cosmic violence. It's sitting about 220 million light-years away, and it is what astronomers call a rich cluster.
Yes, very rich.
We aren't talking about a quiet, settled neighborhood. You have these massive, ancient galaxies actively colliding with one another. And the reason it lit up so brilliantly in X-rays is because of the intracluster medium, the gas between the galaxies.
That gas gets incredibly hot.
Exactly. As these immense gravity wells smash together, that gas is compressed and heated to tens of millions of degrees, causing it to radiate blinding amounts of X-ray energy. It's essentially a massive cosmic pileup happening right in the center of our blind spot.
And the Norma cluster is undoubtedly massive. Its mass is roughly comparable to the famous Coma cluster, making it one of the most massive structures in our local universe. It sits right at the heart of the Great Attractor region.
But it wasn't the whole answer, right?
No, identifying Norma was just the opening chapter. Astronomers soon realized that Norma alone couldn't account for the totality of the gravitational pull.
It was too small.
Right. The real breakthrough came when researchers stopped trying to pinpoint a single massive object and started looking at the overarching flow of gravity itself. This culminated in a monumental paper published in 2014 by a team led by astronomer R. Brent Tully.
Enter Laniakea. I absolutely love this concept. Laniakea is Hawaiian for immense heaven. And the way Tully's team defined Laniakea completely upends how you visualize structures in space.
It really does. Traditionally, the definition of a supercluster was somewhat arbitrary. Astronomers essentially looked for visual densities. If you saw a lot of galaxy clusters clumped relatively close together in the sky, you drew a circle around them and called it a supercluster.
Just a basic grouping.
Exactly. It was a definition based on static proximity. But Tully's team threw that out. They redefined superclusters based on physical dynamics.
How so?
They mapped the peculiar velocities, the actual physical motion we discussed earlier, of over 8,000 galaxies in our cosmic vicinity. They looked at the vectors, they tracked where these galaxies were physically flowing, and they defined the supercluster not as a clump, but as a basin of attraction.
A basin of attraction.
Hmm.
The easiest way to visualize this is to think of a geographical watershed here on Earth.
That's a great comparison.
Imagine a massive mountain range, like the Rockies. The peaks form a continental divide. When rain falls on the eastern side of the ridge, gravity pulls all of that water down into a specific network of streams and rivers that all eventually empty into the Mississippi River Basin.
Right.
But if a drop of rain falls just 1 inch over the ridge, on the western side, it flows into a completely different network that empties into the Pacific Ocean. In space, the individual galaxies are the raindrops. The immense gravity of the cosmic web creates these invisible ridges and valleys. Every single galaxy in our region of space, thousands of them, are all flowing gravitationally toward a single central valley.
Which is the Great Attractor region.
Exactly. That central valley is the Great Attractor, and the entire sprawling watershed basin containing all the rivers flowing into it. That entire basin is the Laniakea supercluster.
And the scale of the Laniakea watershed is just staggering. The physical boundary of this basin is approximately 500 million light years in diameter.
Unbelievable.
It encompasses roughly 100,000 galaxies, including our own Milky Way, which is sitting far out on one of its fringes. To put a number on the gravity driving this flow, the total mass of the Laniakea basin is estimated to be 100 billion times the mass of our sun.
10 to the 17th power.
100 quadrillion solar masses, all participating in a synchronized gravitational collapse toward the center.
100 quadrillion suns. When you look at the 3D maps generated from Tully's data, it's beautiful and terrifying at the same time.
They are incredible maps.
You plot the coordinates, the right ascension declination of these galaxies, and you can literally trace the velocity streamlines. You see the Centaurus cluster relatively close by. To put it in perspective, Centaurus sits at a cosmological redshift of about 0.01.
And we should clarify what that redshift value actually signifies. A redshift, or Z, of 0.01 means the light from Centaurus has been stretched by 1% due to the expansion of the universe during its journey to us.
Right.
In terms of physical distance, that translates to roughly 140 million light years away.
Okay, so Centaurus is at 140 million light years. You see the Hydra cluster around the same distance. Further down the stream, you see the Ophiuchus cluster at a redshift of 0.028, pushing out toward 400 million light years.
Right.
All of their individual streamlines point down into the Great Attractor Valley, funneling toward the Norma cluster. But if you keep looking at these velocity maps, past Laniakea, past our watershed, towering in the background along those exact same velocity streamlines, there is something else.
Yes, there is.
The Shapley supercluster, sitting way out at a redshift of roughly 0.048.
Which places Shapley at an astonishing distance of around 650 million light years from Earth. And that observation basically breaks the original model.
How so?
Because when you map the gravitational flows at that grand scale, you realize the Great Attractor isn't the bottom of the basin.
Here's where it gets really interesting. We spent decades thinking the Great Attractor was the final destination, the ultimate sinkhole pulling us in. But the new velocity maps show that the entire Laniakea supercluster, our entire 500 million light-year watershed, is itself moving.
The whole thing.
The entire basin is being dragged through space. It's like realizing the valley your river is flowing into is actually sitting on a massive tectonic plate that is sliding toward an even bigger ocean.
The architecture of the universe is deeply hierarchical. Gravity operates on every scale simultaneously. We are being pulled by the Great Attractor, but the Great Attractor and the entire Laniakea structure is being pulled by the overwhelming mass of the Shapley supercluster.
Man, we have spent a lot of time building up the myth of the Great Attractor. We started with the spooky anomaly in the CMB, we mapped the dark flow hiding behind the dust of the Milky Way, and we established our place in this colossal cosmic watershed. We've painted a picture of a monster in the dark.
We have.
But just like any good unexplained mystery, the initial theory almost never survives the cold light of new data. Now, is any of this actually true? Are we really being sucked into a dense apocalyptic anomaly?
Well, it is absolutely true that we are moving at 631 kilometers per second. It is true that our local galaxies are flowing together.
Okay, but what about the monster?
The explanation of why we are moving and what exactly the Great Attractor is requires a radical debunking of the monster narrative. There is no singular, unimaginably dense, spooky object sitting in space. There is no giant vacuum cleaner. There is no mega black hole swallowing galaxies.
So what is it?
If we connect this to the bigger picture, to understand the Great Attractor, we have to understand the fundamental physics of the cosmic web, and that requires looking at dark matter.
Ah, dark matter, the invisible scaffolding of reality. It doesn't emit light, it doesn't reflect light, and it doesn't interact with electromagnetism at all.
Right, it's completely dark.
But it has mass, meaning it exerts gravity, and it accounts for roughly 85% of all the matter in the universe. Everything we see, stars, planets, dust, galaxies, is just the 15% icing on a massive dark matter cake.
That's a good way to put it.
But dark matter doesn't just clump into random, featureless blobs. How does it arrange itself to create a gravitational focal point like the Great Attractor?
It forms a highly specific mathematical geometry. The universe is structured like a three-dimensional spider web. At the largest scales, you find vast, incredibly empty regions called voids.
Okay, voids.
The boundaries where these voids meet from expansive, flat, two-dimensional sheets of dark matter and gas. Where those sheets intersect, matter pools into dense one-dimensional filaments, like the threads of a web. And finally, where multiple massive filaments cross each other, you get nodes.
Nodes.
Yes. These nodes are where matter pools to its highest density, forming massive clusters of galaxies.
I was actually reading about the physics behind this, specifically the Zeldovich approximation. This was theorized back in the 1970s by the brilliant Soviet physicist Yakov Zeldovich.
Yes, his work is foundational here.
He was trying to figure out how a relatively smooth early universe collapsed into this intricate web. He realized that the initial tiny fluctuations in the density of the early universe were random, what physicists classify as a Gaussian random field.
The Gaussian random field is crucial here. It implies that the distribution of slightly denser regions and slightly emptier regions followed a bell curve of probability, scattered chaotically.
And because the density distribution was chaotic and random, matter couldn't collapse perfectly inwards into neat, uniform spheres. Gravity isn't pulling equally from all sides.
Exactly.
Zeldovich used the mathematics of fluid dynamics to model this asymmetrical collapse. He showed that a cloud of dark matter will always collapse fastest along its shortest axis. So a lumpy cloud flattens out, forming a massive cosmic pancake.
Which is the sheet we talked about.
Right. That pancake is a sheet. Over time, that pancake then collapses along its second shortest axis, squeezing the sheet down into a dense string-like filament. Finally, the matter flows down the length of the filament, pooling at the intersections to form the nodes.
The fluid dynamic model proposed by Zeldovich perfectly explains our local topography.
So how does the Great Attractor fit into that?
The Great Attractor is not a singular object. It is simply a particularly dense node where several massive filaments of dark matter pulling along thousands of galaxies happen to intersect. It is literally just a busy traffic junction in the cosmic web.
Just a junction.
Yes. However, as our X-ray and radio astronomy improved, measuring the exact mass of the Norma and Centaurus clusters at this junction, astronomers realized something highly problematic for the Great Attractor theory.
What was that?
The mass of the node had been vastly overestimated.
So the monster was actually a lightweight.
Comparatively, yes. When researchers tallied up all the observable mass and inferred dark matter in the Great Attractor region, it only accounted for a fraction of our 631 kilometer per second velocity.
Wow.
Even combined, the clusters at the heart of Laniakea simply do not possess the gravitational muscle to pull us that fast. We had to look further out. We had to look at the Shapley supercluster.
The real heavyweight champion.
Shapley is sitting 650 million light years away, and it is a true cosmic leviathan. It is an exceptionally dense, gravitationally bound collection of over 8,000 massive galaxies.
8,000 massive ones.
Yes. Its central core alone contains 11 major galaxy clusters packed tightly together. To put a number on it, Shapley has roughly 10,000 times the mass of the entire Milky Way galaxy.
That is insane.
The gravity well it creates is so immense that our entire Great Attractor region, the whole Laniakea supercluster watershed, is fundamentally just a tributary falling toward Shapley.
So Shapley is the real driver. It's pulling Laniakea, and we are just along for the ride.
Precisely.
But the universe is endlessly complicated, and the zone of avoidance wasn't done giving up its secrets. Even with Shapley accounted for, the velocity vectors still didn't perfectly align. Something was still missing from the math. And just recently, astronomers discovered another massive player hiding entirely behind the Milky Way's dust, the Vela supercluster.
And the discovery of the Vela supercluster is a masterclass in modern radio astronomy. Vela is hidden about 800 million light-years away, obscured by one of the thickest parts of the galactic plane.
So how do they find it?
To find it, astronomers deployed the Meerkat radio telescope array located in the Karoo region of South Africa.
And Milky isn't a single dish, right? It's an interferometer. It consists of 64 separate, massive radio dishes spread out over miles of desert, all electronically linked together to act as one colossal antenna.
Yes, it is incredibly powerful.
But the key to finding Vela wasn't just raw power. It was what they were listening for. They completely ignored visible light, X-rays, and infrared. They tuned Meerkat to search for the incredibly specific radio signature of neutral hydrogen gas, specifically the 21-centimeter line.
The 21-centimeter emission line is one of the most vital tools in astrophysics. Hydrogen is the most abundant element in the universe. If you can map the vast clouds of neutral hydrogen gas, you are effectively mapping the skeletons of galaxies.
But I want to dig into why hydrogen emits this specific signal, because it's a beautiful piece of quantum mechanics.
It really is.
A neutral hydrogen atom is simple. One proton in the center and one electron orbiting it. Now, both the proton and the electron possess a quantum property called spin, which essentially means they act like tiny little magnets with north and south poles.
Right.
Most of the time, the electron and proton are spinning in the same direction. Their magnetic poles are aligned, parallel. But quantum mechanics says they prefer to be in the lowest energy state possible, which means spinning in opposite directions, anti-parallel.
And when that electron finally flips its spin direction from parallel to anti-parallel, it drops into that lower energy state.
Yeah.
Energy must be conserved, so the atom releases that tiny difference in energy by firing off a photon.
Exactly. But because the energy difference between the two spin states is so infinitesimally small, the photon it fires off has very low energy. Low energy means a very long wavelength. The wave is exactly 21.106 centimeters long.
Which is about 8 inches.
Right. Now think back to the dust grains in the zone of avoidance. Those dust grains are microscopic. When a radio wave that is 8 inches long comes rolling through the galaxy, it is immensely larger than the dust. It passes completely unobstructed through 800 million light-years of space, right through the Milky Way, and hits the Meerkat dishes in South Africa.
By tracking that 21-centimeter signal, astronomers map the hydrogen gas and pierce the densest part of the zone of avoidance.
And what do they find in there?
They discovered 719 massive galaxies grouped together inside the Vela cluster, and less than a third of them had ever been documented before. Vela is an actively assembling giant. The data indicates it features two main dense cores that are currently moving toward each other, meaning the supercluster is still actively collapsing and growing.
And how big is it?
Its mass rivals that of the Shapley supercluster.
So the picture has fundamentally changed. We're not just being pulled by the Great Attractor. We are caught in a colossal, multi-directional, gravitational tug of war.
A huge one.
The Great Attractor is tugging us locally, but the Great Attractor is being ripped toward the Shapley supercluster, while the newly discovered Vela supercluster exerts its own massive sideways pull on the entire system.
But the plot thickens even further. We've spent this entire deep dive talking exclusively about being pulled. Gravity, by its very definition, only attracts matter to other matter. However, the complex mapping of peculiar velocities introduced a concept that seems to violate common sense. We aren't just being pulled towards Shapley and Vela. We are actively being pushed from behind.
Okay, I have to push back on this. Gravity is not magnetism. There is no anti-gravity repelling force in standard mechanics. How can we be pushed?
It sounds impossible.
Furthermore, the papers point to a region called the dipole repeller, mapped by Yehuda Hoffman's team in 2017. They found a vast, empty void directly opposite the Shapley supercluster. How can an empty void, a region with literally nothing in it, exert a physical pushing force on a galaxy? You cannot be pushed by nothing.
It seems highly counterintuitive until you reframe how you think about gravitational fields in a uniform space. To understand the dipole repeller, you must think about relative forces and net vectors.
Okay, lay it out for me.
Imagine you are standing perfectly still, perfectly balanced in the center of a large room. Now imagine there are 100 people standing in a perfect circle around you, and each person is holding a rope tied to your waist. Everyone pulls on their rope with the exact same strength. What happens to you?
Nothing. The forces cancel out. I stay perfectly balanced in the center.
Correct. You feel tension, but your net movement is zero. Now imagine the 10 people directly to your left suddenly drop their ropes. They stop pulling, What happens?
I am violently yanked to the right.
Did the people on your right pull any harder? Did they increase their force?
No, their force stayed exactly the same, but because the opposing force on the left disappeared, the overall net balance of the room shifted. The lack of pull from the left resulted in net movement to the right.
That is the exact mechanism of the dipole repeller. In cosmological models, the baseline of the universe is a uniform distribution of matter. We are situated in a highly unbalanced region.
Unbalanced half.
In front of us, we have a severe overdensity, the Great Attractor, Shapley and Vela. Behind us, Hoffman's team mapped a severe underdensity, a massive void. Because the void lacks the normal baseline amount of galaxies and dark matter, it lacks the gravitational pull that should logically be coming from that direction to balance us out.
I get it now. It's an absence of pull. The net gravitational vector of an underdense region effectively acts as a repulsive force. We aren't being pushed by a magical anti-gravity beam. We are falling away from the void because there's nothing there to anchor us.
Exactly. We are caught in a cosmic push-pull mechanism. The dipole-repeller void is effectively pushing us from behind, accelerating our momentum, while the massive Laniakea, Shapley, and Vela pull us from the front. The combination of the push from the void and the pull from the mass perfectly accounts for our 631 km per second velocity.
That is awe-inspiring. We are surfing a literal cosmic wave. We are pushed by the void of nothingness, funneled down through the Laniakea watershed, past the violent collisions of the Norma cluster, toward these ancient titans, Shapley and Vela.
It's an incredible journey.
But where does this journey actually end? Do we eventually crash into the core of the Shapley supercluster? What is the final destination for the Milky Way?
To answer the question of our ultimate fate, we have to transition from observational astronomy to the absolute cutting edge of computational astrophysics.
Okay, where are we looking now?
In papers published in 2025 and 2026, researchers have begun utilizing next-generation supercomputers to create what they call digital twins of our local universe. These are specifically known as the Manticore local simulations.
A digital twin, meaning they essentially built a perfect 3D simulation of our entire cosmic neighborhood inside a machine to see how it ticks.
Right.
But how do you program the universe? You can't just drop galaxies in randomly.
No, you don't guess. The researchers utilize incredibly complex statistical frameworks, primarily Bayesian algorithms, specifically a framework known as the Bayesian origin reconstruction from galaxies, or the BORG algorithm.
The BB.
Yes. The Bohr algorithm attempts an astonishing feat of reverse engineering. It takes the current, highly detailed astronomical data, the observed positions, masses, and peculiar velocities of galaxies in our local universe today, and it runs the laws of physics backward in time.
Wait, I need to challenge that. How do you rewind 13.8 billion years of gravity? The universe is chaotic. Galaxies merge, gas clouds collapse, dark matter swirls. Doesn't the chaotic friction of billions of years erase the initial starting conditions?
It's a massive challenge.
It's like looking at a puddle of spilled milk on the floor and trying to mathematically calculate exactly how it splashed out of the glass. You can't unspill the milk.
You are identifying the exact problem that Bayesian modeling is designed to solve. You cannot run a simple deterministic equation backward because of the chaos. Information is lost.
Right.
What the Bohr algorithm does is use probabilistic forward modeling. It generates a hypothetical guess of what the early universe's quantum density field looked like right after the Big Bang. It then runs a fast-forward simulation applying gravity and fluid dynamics.
And then what?
It compares its simulated present day to our actual observed present day. If they don't match, the algorithm tweaks its initial guess and runs it again. It utilizes Markov chain Monte Carlo methods to do this millions of times, slowly converging on a highly probable map of the initial conditions of our specific patch of the universe.
So it brute forces the problem until it creates a virtual universe that perfectly mimics our own reality. That is staggering.
Once they have an accurate mathematical model of the past and the present, they possess the power to run the simulation forward. They can fast forward into the deep, unwritten future. And doing so brings us to a massive, fundamental revelation about cosmic flows.
Which is?
This raises an important question. Based on these high-fidelity simulations, is the Great Attractor even a permanent physical structure?
And the simulation results suggest something entirely anticlimactic but deeply profound. The Great Attractor might just be an illusion.
Well, the term illusion might imply it doesn't exist, which isn't true. Mass is certainly there. But it is not a dominant permanent gravitational structure. The Manticore local simulations reveal that the Great Attractor is essentially an artifact of the instantaneous velocity field.
Let's translate that out of physics jargon. Let's go back to a river. Imagine you take a still photograph of a river flowing rapidly over a submerged rock.
Okay.
The water, rushing over the rock, creates a very distinct swirl, a convergence point, where the current dips and eddies right over the stone. If you only possess that single frozen photograph, you might look at that swirl and deduce that the water is permanently drawn to the rock. You might think the rock is the final destination, a sinkhole absorbing the water.
Right.
But if you watch a video of the river, if you introduce the dimension of time, you realize the water just flows over it, it's temporarily diverted by the bump, and then continues flowing downstream to the ocean. The rock is just an intermediate speed bump.
The Great Attractor is the submerged rock. The simulations show that our velocity vectors are highly dependent on the smoothing scale we apply to our data.
Smoothing scale.
It refers to how broadly we average out the gravitational forces over distance. If you look at a small, localized smoothing scale, our immediate motion is just converging on the nearby Virgo cluster. At an intermediate scale, the math points to the Hydra-Centaurus region, which is the classical location of the Great Attractor.
And at the largest scale.
When you expand to a large universe-scale perspective, the flow ignores the Great Attractor entirely and converges firmly on the Shapley supercluster. The Great Attractor is merely a temporary transition point, a local eddy along a much more massive trajectory.
It's just a bump in the road to Shapley. So what is our ultimate destiny? When the researchers run these beyond present time simulations forward, all the way to what they call scale factor A equals 10, meaning a future era where the universe has expanded to 10 times its current physical size, where does the Milky Way actually end up? Do we join the thousands of galaxies inside Shapley?
The results of the A equals 10 simulation are deeply counterintuitive. Despite the monumental pull of the Great Attractor, and despite the staggering combined gravity of the Shapley and Vela superclusters ahead of us, our dominant motion into the deep future actually collapses our trajectory inward.
Inward.
The Milky Way never makes it to Shapley. Instead, we are destined to fall toward the much closer, much smaller Virgo cluster. In the final accounting, Virgo contributes roughly 1/3 of our total local velocity budget.
Wait. We aren't going to the Great Attractor. We aren't going to Shapley or Vela. After all this pulling and pushing from the void and mapping 100 quadrillion solar masses, we just fall into our own local neighborhood. Why? What stops us from reaching the monster?
Dark energy.
The great cosmic spoiler.
The ultimate spoiler. Dark energy is the mysterious, pervasive force that is actively accelerating the expansion of the fabric of space itself.
Right.
For billions of years, gravity has been trying to pull all of these massive superclusters together, spinning the intricate cosmic web. But dark energy operates on an entirely different mechanism. It is stretching the space between the clusters. The digital twin simulations confirm a grim reality. The massive Laniakea supercluster, our entire 500 million light-year watershed, is not gravitationally bound.
The expansion of space is physically stronger than the gravity trying to hold the watershed together.
It is. Over the next several billion years, dark energy will assert complete dominance. It will literally tear Laniakea apart.
That's wild.
The Great Attractor, the Shapley supercluster, the newly discovered Vela supercluster, they will all be pushed away from us by expanding space faster than our peculiar velocity can ever hope to close the gap.
So we can never catch up.
No, we are trying to run toward them on a cosmic treadmill that is constantly accelerating in the opposite direction. Eventually, the Milky Way will merge with the Andromeda galaxy and the local Virgo cluster, collapsing into a single, massive, isolated, elliptical galaxy.
And the rest of the universe.
The rest of the cosmic web will recede beyond our cosmological horizon. The light from Shapley and Vela will simply stop reaching us.
The watershed dissolves, and we are left completely alone. That is a profoundly humbling realization. It makes you think about how incredibly lucky we are to exist right now at this exact fleeting moment in cosmic history.
You really do live in a privileged era.
We are alive when the cosmic web is still dense enough for our telescopes to see our neighbors. We can map out the Great Attractor, we can track the dark flow, and we can mathematically understand the intricate skeleton of the universe.
Yes.
If humanity, or whatever comes after us, had evolved hundreds of billions of years from now, our sky would be almost entirely empty. The astronomers of the deep future will look up and see a blank void. They would have absolutely no way of knowing about Laniakea or the dipole repeller or the Big Bang's background radiation. We are alive precisely at the brief window in time when the universe is most willing to share its deepest secrets.
That is a very poetic way to look at it, but it's completely accurate.
But investigating the Great Attractor leaves you with a final provocative thought. It's a thought about the limits of our knowledge. If the massive Vela supercluster, a structure rivaling the absolute biggest titans in the known universe, was hiding entirely undetected in the zone of avoidance until just a few years ago, and if our entire meticulously crafted map of the cosmic flows is so heavily dependent on our specific, obscured vantage point inside the dusty disk of the Milky Way, what else is out there?
There could be so much more.
What other massive universe-bending structures are sitting right now in our blind spot, waiting for a new telescope to find them? Are there gravitational forces out there lurking behind the galactic center that even the Manticore local supercomputer simulations haven't accounted for? We map the universe assuming we see the whole board, but what if we are still just playing in the dark?
That is the beauty of astrophysics. There is always another horizon.
Always. Thank you for joining us on this deep dive into the cosmic web. We love exploring these massive mysteries with you. If you have any topics you want covered, make sure to tell us in the comment section below. And don't forget to like and subscribe to the Bureau of the Unexplained so you never miss an investigation. Next time you're driving down the highway and you feel the acceleration pressing you into your seat, remember, even with a clear windshield, you are still hurtling through the dark at 1.3 million miles per hour, surfing a cosmic wave you can't even see. See you next time.